Hello everyone, good evening. So this is week 9 for the NPTEL course Introduction to Algorithms and Analysis. This is the problem solving session for the course, and the primary topics covered this week were the introduction and discussion of the BFS and DFS algorithms, so like breadth first search and depth first search algorithms. Then there was a discussion on shortest path problems and how BFS and DFS can be applied to shortest path problems. Then there was a discussion on Dijestra's algorithm. Followed by Bellman-Ford algorithm, right, for graphs with negative weights. Right, so what we'll do as usual is I'll discuss some of the problems and the related theoretical concepts that will help you solve the questions or solve the assignment of this week. So what I'll do is I'll start with some basic examples or basic problems for graphs, and I'll take some problems from previous week as well. So let's start with this problem from last week, that Prim's algorithm is used for what? Is it used to find the shortest path from one vertex to another, or is it used to find the longest common subsequence, or is it used to find the minimum spanning tree for a given graph, right? Or is it used to sort the edge weights? So what is Prim's algorithm used for? Right, so of course, like from lectures we know that Prim's algorithm is an algorithm that is used to find the minimum spanning tree, right? So like the solution for this, we'll just have to remember what Prim's algorithm is used for. But if we discuss a bit what a minimum spanning tree is, right? So for a minimum spanning tree, the input is a connected undirected graph, right, that we represent as a set of vertex and edges, and again it has to be connected. with weight function, right? And that weight function is defined on the edges of the graph, right? So for each edge, there is a real value or a scalar value that is assigned to each edge that is defined as the weight of that particular edge, right? And what we get as the output from the minimum spanning tree algorithm is a spanning tree T, right? So it's a tree that connects all vertices of minimum overall weight, right? So basically the weight, the entire spanning tree is the weight of each edge, right, where the vertices, or the edge you can say, is in the tree, right? So we basically minimize the overall weight, right, of the final tree that is connected, right? And again, we make sure that in a minimum spanning tree we end up with a connected graph, right? So there are no vertices that are like dangling, or there are no two separate trees, right, after we are done with the MST algorithm or the minimum spanning tree. And for forming a minimum spanning tree, right, for a given graph, right, let's take an example from the lecture notes that, right, for, let's say we have a graph, right, with given vertices and some edges, right, and the weights for each edge are this, right? So now this is not a minimum spanning tree, right? So what the minimum spanning tree for this particular graph looks like is what I'm marking in red, right? So a minimum spanning tree again has the same vertices but a subset of the edges of the original tree or the original graph. Right, so if we were to separate it out from the original graph and draw it, right, then this is how the minimum spanning tree of this graph looks like. Right. And again, we can see that it is fully connected, and what we mean by connected, not fully connected, is that the number of vertices equal to the number of edges plus 1, right? Here the number of vertices is 8, right, and number of edges after the minimum spanning tree has been made. So number of edges are 7, right, and then 7 plus 1. So this holds true, right? So that's why there are no cycles in the minimum spanning tree. And if we remove any one edge, then we end up with 2 completely different trees. Right, so that's what a minimum spanning tree is. Okay, and to form this minimum spanning tree, what we use an algorithm called Prim's algorithm. Okay, let's take another example. What is the number of edges present in a complete graph having n vertices? Right, so first of all, we have n vertices, right, and how many edges do we have, right? So for that information, we that's the question, right? And to calculate the number of edges, we need to look at what is meant by a complete graph, right? When do we say a graph is a complete graph? So any graph with vertices v is a complete graph when every vertex has an edge to every other vertex. Right, so if it has an edge like this also has an edge like this. Right, so what happens here is that for every vertex we have n minus 1 edges, right, because there are n minus 1 other vertices for every vertex and it has to connect to all of those vertices, so we have n minus 1 edges. And for n vertices, right, okay, yeah, and also since it has to be connected to all of them, if a vertex has been connected to other vertex, it does not need to connect back, right? So if we start with the first vertex, there will be n minus 1 edges. Then for the second vertex, since one vertex has already been made with the first vertex, right, there will be for first vertex there will be n minus 2 edges, and for the third one there will be n minus 3 edges, and so on. And then between the last two vertices there is just one connection that is remaining, that is 1, right? And this is the total number of edges in the entire graph, right? And we can simplify this using the summation formula that we know, that summation of n, right, is n plus 1 by 2, or we can say summation I and I equal to 1 to n, right? Similarly here it will be n minus 1 times n minus 1 plus 1 by 2, right, because we have n minus 1 entries, it is not a summation till n, right? So the number of edges is n minus 1 times n by 2. And we can see that for a completely connected graph, right, or for a complete graph, the number of edges depends on the square of the number of vertices. Okay, now let's take another example. Consider the undirected graph. Right. And this graph is a set of vertices and edges. And the weights of the edges are here. 9, 10, 7, 26, 22, 4, 5, and 2. Right. What we have to do is, using Prim's algorithm, construct a minimum spanning tree starting with node A. So when we construct the minimum spanning tree, which one of the following sequences of edges represents a possible order in which the edges would be added to construct the minimum spanning tree, right? So for us the options are having EG, then CF, followed by FG, A, T, AB, AC. Or what we can do is we can just get the sequence, right? And then you can just write it here rather than just wasting our time doing this. right? So for this we'll just revisit Prim's algorithm in the pseudocode format. Right. So what we do is we maintain v minus a, right, where a are the is the set of nodes that have been already visited as a priority queue called queue, right? Key each vertex in queue with the weight of least weight edge connecting it to a vector in A. Right, so what we do is we start with our vertex, or like the set of vertices V in the priority queue, right? And we mark the keys for each of the vertex as infinity initially for all the vertices, and for our starting point we mark it as 0. Right, and in our case it is the node A. And what we do is, while the priority queue is not empty, right, we get the vertex with the minimum value of the key for that particular vertex. And then for each vertex that is in the adjacency map or the list, you can say, of U, right? So for every neighbor of U, you can say, right, that has an outward going connection from U, right? What we do is we check if V is in the priority list, right? So if it is not in the priority list, then it has been visited, and the weight between U and V is less than the key, like the current key of U, right? So then we update the key, right, if both of these conditions are true, that the vertex has not been visited before and the weight is less than the current value, right, of the edges. Then we update the key as the current weight, right, and we update the connection, right, the edge for U, it as the one going from U to V. Right, and if we repeat it for till end, like till Q becomes empty, then we basically get the minimum spanning tree, right, from Prim's algorithm. Let us try to now do this procedure for this graph that we have been given here. So I will try to like make things concise and not make too much diagram, so I'll try to keep everything in the same diagram, right? So initially we have all these values, right, all these nodes, and we mark all of them as infinity, right? Now let's say I should use the red one for this, right? And since we have been told that we need to start from A, right, so we mark A as having value 0, right? And then for each of the neighbors, right, and because now Q has all the vertices right now, and A is the first one because we have marked it as 0, so it has the lowest weight or the lowest value of the keys compared to all the vertices. So we start with A, we check for all the vertices of A, right, and since the vertex, let's say we start with B, then we go to C, and then we go to D, right? So for B, right, so B is actually in Q, right? B has to be explored right now, right? And the weight between A and B is less than the key of U, right? Is it so? No, right? So yeah, of course, since the weight is less than the value of nu, okay, so yeah, here we compare with the value of key of nu, right, of the adjacent node, right? So now we can see for this example, B will have a value of 10, right, and C now will have a value of 22, and D will have a value of 7. Right, and now since we have to make an edge between these, so again we start by let's say A has now been explored, right? So A is now out of the queue, right? So the next ones that we are going to explore is basically D, right? Because now for out of all the values that are there in the graph, right, or that are there in the priority queue, right, and in priority queue A is not there now, so the next value will be D because it has the minimum weight, right? And then for D we will do the same comparisons, right? For D the adjacent are A, C and F, right? So for A is the weight between A and D less than the weight of A, right? It is not, right? So this has been checked from both ends. And for C again, is the weight between D and C less than the value at C, right? No, right? So we leave it as it is, and then we check the value between D and F, right? Of course, F will be updated to 22, right? And now D is also out of Q, right? D is also kicked out of Q. And now the next, right? So the first edge that has formed for us, right, is A comma B. Okay. Now for the next iteration, we see that the next vertex will be B, right? Because it has again the minimum value out of all the vertices in the primary queue, right? So again we check between A and B. This does not get updated, right? So we have a vertex between A and B now. Okay, so the first one was between A and D, right? Followed by between A and B, right? And for B there are like 3, right? A, C and D, like, so we check for all 3, right? So 30 is greater than 22, we do not update C, and of course 49 is less than infinity, so we update E, right? So now B is also out of the priority queue, right? So the next one will be now, since there is a collision between the values, right, for C and F, so because it was priority queue, so if we check for all the values between the priority queue, we'll get C first and then we'll get F, right? So F will be the last one that we end up with, right? Because it has the minimum value and it is at the last of the priority queue. Okay, so let's say we take F, right? So for F, we don't update the connection with D, right? Because 22 is more than 7. Right, we are now doing it for F. And for C, the value of C is now updated when we start checking from F. And for G, the value is updated to 5. Right, so the new edge that is added is between D and F. Right, so now in the next iteration, the C has minimum value, right? So we check for the adjacent vertices of C, right? So all the other vertices except G are the adjacent vertices, so we check all of them, right? So for A, the weight is larger than the key of A, and like again, A, B and D are A, B, D and F are already explored, right? So we should only be exploring E. Okay, so E gets updated to 10, and of course we should also have an edge here, right? Because this edge should have formed when we were checking for F, right? So CF is the next edge. CF or FC, like however you want to see it. Okay, so we do this. Now C is also out of the picture. We end up at G, right? Because now it has the minimum value that is at the priority queue, right? So for G, F is not updated, right? Because F again is the adjacent of G, right? And it doesn't matter if G is in or F is in priority queue or not. We have to check all the adjacent values. So the next edge that is formed is between F and G, right? And for E, again the value gets updated to 2, right? And the last edge again will be between E and G, right? When we start looking at E. Okay, so we take the least value. So the last edge is between E and G, right? So this is the order in which edges are added for forming the minimum spanning tree according to Prim's algorithm, right? For the problem that we took. Okay, let's now take another example. Correct choice of data structures can improve the performance of algorithms. Match the following algorithms with appropriate data structures, right? So we have BFS, then we have DFS, and then we have sorting, right? And which data structure is basically better for which algorithm, right? So basically we need to know how does the algorithms work, right? So for breadth first search, right, what we end up doing is we first search at all the elements at a particular level within a graph, right? And a level is defined as the number of edges required to reach that particular vertex from the starting or the source vertex, right? So let's say we have a graph like this, right? And we start from this node, right? And then we, let's say, want to search for the G node, right? So how we go about in the breadth first search is basically, again, we make a priority queue, right? So the priority queue is, starts from the node S, right? And what we do is when we start processing, like when we start searching, we pop this node S, right? Let's say U is equal to S, and we pop S from Q, right? So, and then for all the neighbors of S, right? Or you can say the adjacent vertices of S, or we should say U, right? What we do is we insert U to Q, right? For all the neighbors, and then we do like the same, right? Because now Q will end up with, let's say, V1, V2, right? Or we can write A comma B, where this is A, B, C, D, E, F, G. We already have an H, right? So now next, so first we searched at this level, right? Let's say this first level, and then we will search for A and B, right? And we search for A, we get nothing, we put A out. When we start searching for B, right, we get these, right? So basically the next level, D, C and E, right? So again we put D, C and E in this Q, right? And then we throw B out, right? Not D, right? And then we start searching for D, right? And when we are searching for D, right, and B is now a visited node, right? So all these nodes are visited, so we don't look at them, right? So when we are searching for D, the next adjacent is F, right? So we add F, and then we get done with D, right? And then we go through C, right? And when we go through C, there is nothing to add, and then we go through E, right? And when we go through E, we end up adding G, right, to the graph or to the queue. Now you can see that this is very simply a first in kind of structure, first in first out, right? So we process the values in the same order that they were added in to the queue, right? So since A was the first one in, it was the first one out, and same for the next consecutive vertices that were added to the priority queue, right? So this is basically a queue data structure, right? So for BFS, we prefer to use a queue kind of data structure because that is how the algorithm works also, because we need to process the nodes as they keep coming in, right, based on the depths of the nodes. Let's say this and then this. And similarly for depth first search, what we do is we do last in first out, right? So if our priority queue has, let's say, A, right, so we want to process A, right? So we take A out, and we have S in the starting, right? So we take S out, this is empty. Now this is populated with A and B, right? Now what we do is we take the last added value in the priority queue, right, and then process that, right? So when we were trying to process B, we added, let's say, in the same order, C, D and E, right? Now we process E, right? Like the last added value is processed first, right? So after E, we process G, and then when we process G, we are done, right? So again, due to the structure of the graph, we can simply see that DFS takes lesser number of iterations of finding the goal node as compared to BFS, right? But that's just the difference of the two algorithms that was apparent in this example as well. And the data structure or the type of queue that it maintains is a LIFO, right? Last in is the first out, right? And this is a stack data structure, right? So DFS, for DFS we use stack, right? Because stack is better for DFS. And then for sorting, of course, we know from before that we prefer heap, right? Because we need to do dynamic allocations to form our recursive trees and to form our auxiliary arrays. Let's take one more example. So Bellman-Ford algorithm can be applied for which kind of graphs, right? Undirected and weighted graphs, directed and weighted graphs, undirected and unweighted graphs, or just all directed graphs. Right, so of course we know that Bellman-Ford algorithm, right, can be applied for all directed and weighted graphs. Where the weight function right for some of the graphs can be positive or negative, right? So the graph needs to be directed and weighted for us to be able to use Bellman-Ford. So I think all these problems that were discussed, they will help you understand these concepts better that we have discussed right now. It will help you also understand some of the algorithms that we discussed. So I'll stop the meeting here. Thank you.